Hi, I am Cephas Barreto, a PhD student from Brazil, and I will present work entitled Investigating the Use of a Distance-weighted Criterion in Wrapper-based Semi-supervised Methods. This presentation is organized as follows: a brief introduction, the proposal, the methodology, the obtained results, our conclusions, and the acknowledgements. Semi-supervised methods were designed to solve classification problems where labeled data are expensive or difficult to obtain. The wrapper-based SSL methods are generally iterative and based on the selection and labeling of instances. Despite the wide range of application and good results, wrapper-based methods can select or label instances wrongly. This problem occurs as a snowball effect, since problems that occur at the beginning propagate for each new iteration. Based on this fact, improving a wrapper-based SSL method is strongly related to the investigation and the advancement of the selection and labeling steps. Most selection and labeling criteria used in SSL are generally related to the confidence and distance metrics. In addition, recent work proposed using the agreement from a pool of classifier as a criterion in wrapper-based methods. In previous work, we presented the distance-weighted criterion, a selection criterion that combines confidence and distance metrics. Despite its use in selection, it's also possible to use this criterion for labeling and apply it in any wrapper-based SSL method. As the distance-weighted criterion allows the combination of two criteria, it's also possible to use the agreement from a pool of classifiers combined with distance for selecting and labeling instances in wrapper-based methods. In this work, we investigate confidence and agreement combined with distance as criteria to improve the results of wrapper-based methods. To analyze the impact of DWC in semi-supervised methods, we present our work entitled Investigating the Use of a Distance-weighted Criterion in Wrapper-based Semi-supervised Methods. The self-training method follows an iterative sequence: training with the labeled set, classification of the unlabeled set, selection of the best classified instances from the unlabeled set, assigning labels to the selected instances, joining them to the labeled set. This process is repeated until the unlabeled set is empty. In the standard version of self-training, selection and labeling are performed based on confidence from the main classifier. As mentioned, we develop a distance-weighted criterion that combines two criteria, as distance and confidence. The self-training versions based on DWC confidence follow the same sequence as a standard self-training, changing only the criterion used for selection in version S, for selection and labeling in version SL, and labeling in version L. All the process from the original algorithm stay based on confidence, as in the standard version. Three self-training versions use the distance-weighted criterion based on agreement. They all have the selection and labeling steps based on the agreement from a pool of classifiers. The S version performs the selection process using the DWC criterion. In version SL, selection and labeling are performed using the combined criterion. And finally, in version L, only the labeling is performed using the agreement weighted by distances. In these versions, all other processes are based on agreement only. The experiments were executed over 35 well-known datasets with different characteristics. For performance evaluation, 10 executions of tenfold cross-validation methodology were performed over each dataset, all with the same hardware configuration. In relation to the methods, in the first analysis we compared 8 self-training versions, 2 baseline versions, 3 confidence versions, and 3 agreement versions. In the second analysis we compared the 2 best proposed self-training versions against 2 graph-based SSL methods and against 1 supervised method using 2 training strategies. As a performance metric, we adopted accuracy, and all the code was based on the Weka API. Our methodology for using a fully labeled dataset in a semi-supervised experiment is composed of these steps: shuffle the dataset, split the dataset in 10 stratified folds, separate fold 1 for validation, divide the remaining folds 2 to 10, use 10% for the labeled set L and 90% for the unlabeled set U. Run the self-training implementation using U and L, validate the built-in model using V and save results. Repeat steps from 3, changing the fold used for validation until all folds have been used as validation. These steps represent an execution of tenfold cross-validation methodology. In the first analysis, which compares standard and random selection versions of self-training with the 6 proposed DWC versions, the results show that version STDWC-AL, based on agreement that performs the labeling using the DWC criterion, obtained the best result, with 73.40% of accuracy, 2.89 in average rank, and 12 wins. This method won in 3 out of 3 criteria. This result was statistically similar to the following 4 beta self-training versions, as observed in the CD diagram. In the second analysis, we compared the 2 best self-training versions with benchmark methods as graph-based methods LLGC and GRF, plus 1 supervised method using 2 training strategies. The results of this part show that the supervised method J48 obtained the best results in 3 out of 3 criteria: accuracy, rank, and wins. Despite that, the performance of STDWC-AL, the best proposed method, was in second place and was statistically similar to the supervised method. This result reinforces the expected superiority of the supervised method trained with 90% of the dataset. Still, it points out that using a more elaborated criterion such as DWC can bring a semi-supervised method to the level of a supervised method. In general, we can state that the proposed approach positively affects self-training's performance, especially when the distance-weighted criterion, confidence or agreement was used in the labeling process. Moreover, it's possible to affirm that the proposed version surpassed the performance of J48 10% and graph-based SSL methods. Despite the superiority of J48 training with 90% of the dataset, the statistical analysis pointed out that the proposed version STDWC-AL obtained a similar performance. I want to thank the professors and students who helped me with this work and CAPES that partially supported this research. Thank you for watching, and please let me know if you have any questions.